Okay, in this video, it's continuation of the previous one, MATRICES-7. Here we do some more questions on mathematical induction, or rather matrix questions which are to be proved using mathematical induction. So here you have another question. It says, let A be this given matrix. Let A be the matrix 0, 1, 0, 0. And the question is to show that AI plus BA the whole raised to n. And when you read it, as you read it, you should know what is a matrix and what is a scalar here. So A is a number into the identity matrix. And since A is a 2 by 2 matrix, we know that this I is a 2 by 2 matrix, 1, 0, 0, 1. So A is a number into I, the identity matrix, plus B is a number into A, the given matrix, to the power of n is going to be A raised to n into I plus n times A raised to n minus 1 BA. So that's the identity we need to prove. And since this result is true for n, it's not mentioned here, n is a positive integer. So since the result has to be proved true for every positive integer, we use mathematical induction. And we know the steps involved in it. First thing is the result to be proved I call as Pn. So that's a result to be proved, and so I name it as Pn. So I'll say let Pn be this result which is to be proved, where n is any positive integer. And using the principle of mathematical induction, we know that there are 3 different stages. So the first stage is to assume that n is equal to 1. We take the value of n as 1 and show that this result is true for n is equal to 1. Which means I should work out what is the LHS when n is equal to 1. Then I should work out the RHS when n is equal to 1 and show that both the values are the same. So I start with the LHS. LHS is AI plus BA the whole raised to n, where n is 1. So it is AI plus BA the whole raised to 1, which is AI plus BA. Nothing happens to it, and that's the LHS. Now I'm going to work on the RHS. So I'm going to copy the RHS and make n as 1 there. So that's my RHS, but I made n as 1. So A raised to n into I became A raised to 1 into I plus n into A raised to n minus 1, but n is 1. So it's 1 into A raised to 1 minus 1, 1 into A raised to 0, and then B and A I copied. And I know that A raised to 0 is 1, so that makes it AI plus BA. So I got the same answer, AI plus BA, on LHS as well as RHS. And so since they are equal, so LHS equal to RHS, so LHS and RHS are equal, which means the result to be proved, that's Pn, is true for n is equal to 1. So we actually proved that the result Pn is true when n is equal to 1, or rather P1 is true. So that's the first stage of the question. In the second stage, since we have already done a question, you will remember, the second stage we make an assumption. So we'll say that the result is, assume that the result Pn is true for n is equal to k, or rather I just say pk is true, which means the result is true, the result Pn is true when n is equal to k, that's pk is true. So we assume that the result is true for n is equal to k, that is pk is true, which means into this result, wherever n comes, I can put k where k is any integer. So I'll say therefore ai plus ba the whole raised to k is equal to A raised to k into I plus k times A raised to k minus 1 BA, equation number 1. And I should actually mention here that k is a positive integer where k belongs to z plus. I forgot to write that. You should definitely add that. Maybe I can just quickly add it there. So I'm going to quickly add that result which I missed here. So I'm going to say k belongs to z plus. K belongs to z plus. Okay, so we anyway we assumed a result. We assumed that the result is true for n is equal to k. We move on to the third stage, and in the third stage we say, now under this assumption, assuming that pk is true, we are trying to prove that pk plus 1 is true, which means the result is true for n is equal to k plus 1. Now to prove that pk plus 1 is true. Now what's the meaning of pk plus 1? Wherever k comes, I should replace this k everywhere by k plus 1. So I'm going to say that is to prove. This is not proved, we are going to prove. We say that means I'm supposed to be proving that this result is true for n is equal to k plus 1, which means wherever k comes, or rather n comes, I replace it by k plus 1. So ai plus ba the whole raised to n became k plus 1 is equal to a raised to k now became a raised to k plus 1 into I, plus k became k plus 1 into a raised to k plus 1 minus 1 is k there into b and a. This is what I have to prove. And anything I need to prove, we have a standard approach. This is what I had to prove. I'm just copying that one more time, what exactly I'm supposed to be proving here. I just copied it. And to prove that, I'll start with the LHS. So let me copy the LHS. LHS is ai plus ba the whole raised to k plus 1. But I know k plus 1 means ai plus ba the whole raised to k into ai plus ba the whole raised to 1. A raised to m plus n is a raised to m into a raised to n. So a raised to k, this ai plus ba the whole raised to k plus 1, I split as ai plus ba the whole raised to k into ai plus ba the whole raised to 1. But when I split it this way, this I have already seen somewhere. ai plus ba the whole raised to k is my pk by equation number 1. We already have an answer for this in equation number 1. So we go back to equation number 1 and then look at what was ai plus ba the whole raised to k, which I am going to copy here. This is from equation number 1. I replace this ai plus ba the whole raised to k by its value from equation number 1. And the second term, ai plus ba the whole raised to 1, which means ai plus ba, I will copy as it is. But this is done from equation number 1. And remember, that was an assumption. So we made use of our assumption to get this step. The next step is it is multiplication of binomials. I'll take this first term and multiply both in the next bracket, then take the second term and multiply both in the second bracket, probably like this. Look at this arrow mark. A raised to k into I will go with the first term, a raised to k into I will also go with the second term. Then I'll take the second term and do the same thing. So like that, it goes with the first term and it goes with the second term. So let's start multiplying. It's going to be a raised to k I into ai. A raised to k into a, the numbers I am multiplying first. A raised to k into a raised to 1 is going to be a raised to k plus 1. And then I into I. I is an identity matrix. I into I is I again. I into I, identity matrix into any other matrix should give me the same matrix. So I into I should give me I. Now again, a raised to k I goes with the second term. A raised to k into b, the numbers, a raised to k into b, a raised to k b, then I times a is a. A raised to k into b is a raised to k b, and I into a is a. So with the first term, I multiplied both the terms in the next bracket. I'm taking this second term, and with that, again I distribute it in. This second term, I'll multiply inside the next bracket. So I'm going to multiply with this term here. So let's look at it. This k, there is no other k term there, so it's going to be k itself. Then I have this a raised to k minus 1, which gets multiplied by a raised to 1. A raised to k minus 1 into a raised to 1. Should add up the powers. So a raised to k minus 1 into a raised to 1 is a raised to k minus 1 plus 1, which will give me a raised to k. Then b will stay as it is. Then a into I, a matrix A into identity matrix is A itself, plus. Now this term goes with the last term. The k would stay the same, a raised to k minus 1 will stay the same, b into b will be b square, and a into a will be a square. So let's write that term. K stays the same. A raised to k minus 1 stays the same. This b into b makes it b square, and a into a makes it a square. I'm trying to simplify this a bit. The first term I copy as it is, and there is also another reason. And that's one of the terms I need there, and I already have it here. I wrote it. If I look at the second and the third term, there is something common in it. A raised to k ba. That much is common in these two. So I'm going to take a raised to k ba common out. And if I take that out, what is balance here? A raised to k ba is completely gone out, so that's going to be 1 plus k. So 1 plus k, I have 1 here and k there. So 1 plus k, of course I wrote it as k plus 1. 1 plus k into the common factor which I took out, a raised to k ba, plus, oh no, hold on, look at this. This is exactly what I am looking for. I already have my right hand side. This is what I am supposed to be proving. What do I do with this extra term? So then my common sense says that it has to turn out to be 0. So I just wrote 0. But how can it be 0? K is any positive integer, not 0. A cannot be 0 according to the question. Then the question doesn't exist. B cannot be 0. And the only possibility is that this a square could be 0. So I'm going to work out what is a square. What is a square? A multiplied by a again. A matrix which is given in the question into a again. So I'll do matrix multiplication. Row goes with the column, 0, 1 goes. First row goes with the first column. 0 into 0 is 0 plus 1 into 0 is 0. So that's 0. Then the first row goes with the second column. 0 into 1 is 0 plus 1 into 0 is 0. So you get every element there 0, which is represented by 0. So that's a 0 matrix. So that's how the very last term became 0. And that means I have my RHS. So I started with the LHS and I reached the RHS, which means I proved that pk plus 1 is true whenever pk is true. Remember, pk plus 1 is true if pk is true. But we have already proved that p1 is true. We already proved it. If pk is true, then pk plus 1 must be true, we proved. So if p1 is true, then p1 plus 1, that is p2, has to be true. Now that p2 is true, I go for this again. p2 is true, therefore p2 plus 1, that's p3 is true. It is true for 3. And if it is true for 3, p3 is true, it has to be true for p3 plus 1, which is p4. P4 will be true. So it just goes on like that, and that's called a mathematical induction. Therefore, by PMI, the result Pn is true for all n belongs to Z plus, which means positive integers. You should take your time to slowly write it down, pause the video, write it down, go back, copy it down, try to understand it, listen to what I am saying here again, and then learn it. We're going to look at another question. If A is equal to cos theta sin theta minus sin theta cos theta, then prove that A raised to n is equal to cos n theta sin n theta minus sin n theta cos n theta. Actually, the result looks very interesting. Like if I need to do a square, it's going to be cos 2 theta sin 2 theta minus sin 2 theta cos 2 theta. If I want a to the power of 10, it would be cos 10 theta sin 10 theta minus sin 10 theta cos 10 theta. Very interesting results. We are trying to prove that. And since this result is true for all positive integers, actually my question is incomplete. I should be saying where n is any positive integer. So I'm trying to prove this result for every positive integer. So that's done by the principle of mathematical induction. This is the result I have to prove. So I'm going to call that as Pn. So I'll say let Pn be this result which we are supposed to prove. A raised to n is equal to cos n theta sin n theta minus sin n theta cos n theta. A raised to n is equal to. So that's the result I need to prove. And stage 1. We assume that n is equal to 1 and we'll work out the LHS. What's the LHS? LHS is a raised to n, but n is 1. So a raised to 1 is a. So the LHS is a. And now I do the RHS. What is RHS? RHS is cos n theta, but n is 1. So cos 1 theta, sin 1 theta, minus sin 1 theta, cos 1 theta. But that, if you go back and check your question, that's actually your a. So RHS also becomes a. So LHS was a, RHS is also now a. So LHS equal to RHS, which means we proved that the result is true for n is equal to 1, or rather P1 is true. Stage 2, where we make an assumption. So we'll say assume that Pk is true. What's the meaning of it? Assume that the result is true for n is equal to k. So into the result which is to be proved, into this Pn result which is to be proved, I just assume that this result is true for n is equal to k. It simply replace n by k and I have this, which is an assumption. We didn't prove it. We just assumed that the result is true for n is equal to k, where k is, I should mention that, where k is any positive integer. So I assume that the result is true for any positive integer, any random positive integer. But what we are going to do now is, in stage 3, that it is also then going to be true for the very next integer k plus 1. Assuming that the result is true for n is equal to k, we want to prove that it is going to be true for its very next number k plus 1. So stage 3 will say, now to prove that pk plus 1 is true. That is, to prove, we haven't proved it yet, we just say that is, we need to prove this particular relation now. This is what I am supposed to prove. That is to prove that a raised to k plus 1 is equal to cos of k plus 1 theta, sine of k plus 1 theta, minus sine of k plus 1 theta, and cos of k plus 1 theta. This is exactly what I have to now prove. So, but that, remember, we are trying to prove this under this assumption, which means by making use of equation number 1, I should prove this result. Let me copy what I have to prove one more time, my pk plus 1 result. That's the result I have to prove. And to prove any result, I need to start from the left side, and then, so I'm copying the LHS, which is a raised to k plus 1, which is a raised to k into a, and I need to finally reach the right hand side. When I split it as a raised to k into a, this a raised to k is there in equation number 1. That's my assumed result. I assumed that a raised to k is equal to something. So I go back to my equation number 1 and copy that expression. So let me copy that. Cos k theta sin k theta minus sin k theta cos k theta into a. A is there in my question, so I copy that as well. A 2 by 2 matrix into another 2 by 2 matrix will get me a 2 by 2 matrix again. The row goes with the column. The first row goes with the first column, first row goes with the second column, then we repeat it with the second row. So let's multiply. The first row goes with the first column. So it's going to be the first row going with the first column. How does it go? Cos k theta into cos theta, cos k theta, cos theta. See, first row goes along the first column. Cos k theta into cos theta plus sin k theta into minus sin theta, minus sin k theta sin theta. Look, first row goes with the first column. Cos k theta into cos theta plus sin cos k theta into minus sin theta, which is written as minus sin k theta sin theta. The first row goes with the second column. Cos k theta into sin theta plus sin k theta into cos theta. So that's my second term there. Now the second row goes with the first column. Minus sin k theta cos theta plus, then multiply cos k theta with minus sin theta. So this is what I have. Carefully you should do that yourself and see. Minus sin k theta into cos theta plus cos k theta into minus sin theta minus cos k theta sin theta. Now the second row goes with the second column, minus sin k theta plus cos k theta cos theta. So that's my last term. Carefully, you have to multiply that yourself and see. But when we try to study this, it is all known formulae. Look at the first one here. It looks like cos A cos B minus sin A sin B. Cos A cos B minus sin A sin B. Cos A cos B minus sin A sin B is cos of A plus B. Cos k theta cos theta minus sin k theta sin theta is cos of A plus B. Cos of k theta plus theta. So that is cos A cos B minus sin A sin B formula. And what is this? This is sin A cos B. I read this term first. Sin A cos B plus cos A sin B. Sin A cos B plus cos A sin B, sin of A plus B. So that's going to be sin of k theta plus theta. Down here, if I remove a minus n out, it is again sin A cos B plus cos A sin B, which is sin of A plus B. Of course, with a minus n outside, sin of k theta plus theta. So minus of sin of k theta plus theta. Here again I will read it this way, cos A cos B, this term first. Cos A cos B minus sin A sin B is cos of A plus B, cos of k theta plus theta. If I take a theta common factor out, it's going to be cos of k plus 1 into theta, sin of k plus 1 into theta, minus sin of k plus 1 into theta, and this is cos of k plus 1 into theta, which is exactly same as the right hand side, what I am trying to prove. So I got LHS equal to RHS, which means pk plus 1 is true whenever pk is true. So because we made use of equation number 1 here, so since we made use of 1 here, we know that we proved pk plus 1 under the assumption that pk is true. But we already proved that p1 is true. Therefore, by principle of mathematical induction, the result is true for all n belongs to the set of natural numbers. This particular question, I'll just give you a small hint in the beginning, and then you should go ahead and pause the video. You should try to do it yourself, but I will also complete it. You can watch it after you make an attempt to do this yourself. Look at this question. There is a matrix A here. It's a 3 by 3 matrix with every single element as 1. And I need to prove that A raised to n is then going to be a 3 by 3 matrix again, but every single element is 3 raised to n minus 1. Interesting. A is 3 by 3 matrix with every single element as 1. A to the power of n would be 3 raised to n minus 1 comes in every place in the 3 by 3 given matrix. So it's again a 3 by 3 matrix, but every single element is going to be 3 to the power of n minus 1. Just for the sake, just to see what is A raised to 100 then going to be. It would be 3 raised to 99 everywhere. So that's the meaning of this question. Very interesting question. Okay, so we are going to prove this by mathematical induction. So this is the result to be proved. What I'm going to say is I'm going to give you one small suggestion before you start doing this yourself. I'll say let P and B, A raised to n is equal to, this is my A raised to n, but I didn't copy like that. I saw that every single element inside this 3 by 3 matrix was the same, 3 raised to n minus 1. So I took 3 raised to n minus 1 out, and then I have 1, 1, 1, 1, 1, 1, and 1, 1, 1. That's your Pn. Don't take this, the simplified format. Now you try to do this question, I'm sure you will be able to get this answer. So you should pause the video now. Try to do this yourself. In case you are not able to prove it yourself, come back and watch this. So I'm continuing it now. Stage 1, we say n is equal to 1. Then I'll work out the LHS. LHS is A raised to 1, which is A. And what's A? That matrix. A 3 by 3 matrix with every single element as 1. I'll now do the RHS. What is RHS? 3 raised to n minus 1 into this matrix. But 3 raised to n minus 1 is 3 raised to 1 minus 1, which is 3 raised to 0. And 3 raised to 0 is 1. So I just get the same matrix with every single element as 1. So I have my LHS, RHS coming the same. So I say LHS equal to RHS. and therefore P1 is true. Stage 1 is over, and what is stage 2 now? In stage 2, we make an assumption. And what's our assumption? We assume that the result is true for n is equal to k, or rather pk is true. So what's the meaning of pk? Into this pn, wherever n comes, I put k. So that is a raised to k is equal, I just make n as k. So 3 raised to k minus 1 into this 3 by 3 matrix with every single element as 1. That is the assumption we make. And don't forget the fact that k stands for any positive integer, is that plus. So this is our assumption. We assumed that the result is true for n is equal to k. In stage 3, then what am I supposed to do? In stage 3, I should assume that the result is going to be true for the very next integer, which is k plus 1. So that's my stage 3. I just copied my equation number 1, the assumed one. Now to prove that a raised to k plus 1 is true, that means I need to prove that a raised to k plus 1, okay, small correction here. I said now to prove that a raised to k plus 1 is true. That's not the correct statement. What I have to do is pk plus 1 is true. So what I should have written was now to prove that pk plus 1 is true, not a raised to k plus 1. So not that. So I'm supposed to prove that now to prove that p of k plus 1 is true, which means the result is true for the very next integer k plus 1. So what is a raised to k plus 1? A raised to k plus 1, replace k by k plus 1. That's what we have to prove. So a raised to k plus 1 is equal to 3 raised to k plus 1 minus 1, which is 3 raised to k into this matrix remains the same. This is what I have to prove. And to prove anything, I start with the LHS. So what's the LHS here? A raised to k plus 1, which is a raised to k into a. But what is a raised to k? I know from equation number 1, so I'm going to copy that. So my a raised to k I copied from equation number 1 into a, which is there in my question, the 3 by 3 matrix with every single element as a, as 1, which I copied here. And it's a 3 by 3 matrix into 3 by 3 matrix, which I'm going to multiply and get the answer as another 3 by 3 matrix. The first row goes along the first column, 1 into 1 plus 1 into 1 plus 1 into 1. That's 1 plus 1 plus 1, which is going to be 3. And when I do first row into the next column, I get again 1 into 1 plus 1 into 1 plus 1 into 1, which is again 3. And the first row into the third column, I'll get 1 into 1 plus 1 into 1 plus 1 into 1. So I'll get 1 plus 1 plus 1 everywhere in all the 9 places. So isn't that 3? So I save some time by writing them all as 3. So which means this matrix gives me a 3 common factor, which comes out. You have a 3 raised to k minus 1 outside into another 3. 3 raised to k minus 1 into 3 raised to 1 makes it 3 raised to 3 raised to k. And then I have only balance 1, 1, 1, 1, 1, 1, which is what I was supposed to get on the right side. So my LHS equal to RHS, which means I proved that pk plus 1 is true whenever pk is true. So I could prove that pk plus 1 is true because we assume that pk is true. So if pk is true, then pk plus 1 has to be true for the very next integer. But in the beginning, we already proved that p1 is true. And if p1 is true, then it has to be true for p1 plus 1, which is p2. The result is true for n is equal to 2. Now if p2 is true, it has to be true for n is equal to 3. p2 plus 1, 3. p3 is true, then it has to be true for the very next integer 4. p4 is true, it has to be true for 5, and so on. It never ends, which means the result is true for every positive integer, and that is called the principle of mathematical induction. So by principle of mathematical induction, the result is true for every positive integer, or n belongs to z plus. You have a question? So let me complete this question. As I finish writing this question, you'll copy it down, you will pause the video, copy it down, try on your own. If you are unsure of this method still, I would suggest that you watch this video again slowly and write it down. Eventually you will learn it.